All right, thank you. Is this mic okay? I think we're, yeah, all right, good. Well, thank you very much. Welcome to IUI 2016. We are the general chairs. I'm Jeff Nichols, Joel Mahmood, John O'Donovan. And we're really excited to see you here. Very nice. Oh, and also our papers chairs, sorry. Christina and Massimo. Really excited to have you here. And I'll let Joel continue with the welcome presentation.
Thank you. Welcome, everyone, to IUI 2016. We are excited to have you here at beautiful, sunny, but it was likely to be sunny, but rainy Sonoma. So we first want to thank to all our sponsors and supporters like ACM, SIGCI, SIGAI, AAAI. Also, we have corporate supporters, gold sponsor, Microsoft Research. So we really appreciate their help and support. Silver sponsor, Google and IBM. We thank them for their continuous support for IUI and hope that that will continue. And bronze sponsor, Tableau Software. We also want to give a big thanks to this awesome organizing committee. There are 19 of them. People have different roles, like from program chairs and poster demo chairs, workshop chairs, registration, and all those different roles. You can go and see in the committee page in the website. But here are their photos. If you see any of them here, some of them on the stage, some of them in the audience, say thank for all their great work for this conference. Without their help, we would not be able to achieve where we are now. So a big thank to all of the organizing committee members. So I will hand over to John to continue from the next slides.
So yeah, as Jalal said, welcome to sunny Sonoma. We can't control the rain. I'm really happy to welcome, just to speak a little bit about the local area, Johnny Westham, who's the director of the Visitors Bureau here in Sonoma. So he's going to tell you a little bit about the local area.
Cool. Thanks for having me. Thank you, John. Good morning. My name's Johnny Westham. I'm the executive director of the Sonoma Valley Visitors Bureau here in Sonoma. Beautiful, rainy Sonoma. I mean, it is California, but California is also under a drought, so we are praising that we have this type of rain coming in town. Over the course of February, we received very, very, very little rain, and as a result of December and January, our water levels are starting to rise again. So this rain is welcome, but I tell you what, in wine country, it doesn't matter what the weather looks like, it's still beautiful. It doesn't matter what time of year it is, if it's spring, if it's fall, if it's summer, it's still beautiful. And the funny thing is, I'm up here from Southern California. I just moved up in July, and it was big leaves on all the vineyards. The trees were all green. It was a real full destination. And somebody came up to me and said, wait till fall happens and then wait till winter happens. I said, I can't wait for that. You know, all the leaves are going to be dead. They're all going to be on the ground. It's all going to be nasty. It's going to look dead in this destination. And then it happened. The red trees came out. The green trees came out. The orange trees came out. The leaves fell off, but then you could see these rows of flowers. And I said, this is one of the most beautiful destinations in the world. So you guys are in for a real treat being in Sonoma and Sonoma Valley. So a quick history on Sonoma Valley. It was actually settled by the Mexican government and the Mexican army in the early 1800s. General Guadalupe Vallejo actually settled here and brought the missionaries who were building the missions along the west coast. And this is the northernmost mission, which also is part of the San Juan Capistrano, the San Diego, the ones in Santa Barbara, the ones in San Luis Obispo, and so on and so forth. So this is the northernmost mission that the Mexican government actually settled. And then the Russians came down through the Russian River, and then they retracted after they found that the Mexican army was much larger than they were. So this is actually a battleground here, and the battleground continues to grow as this was where California became a state, and they settled over the Mexican government, or the United States settled over the Mexican government here and claimed California as a state. And then they had a big fight at the state level, and that's where the bear flag, or the California Republic flag, was actually found as well. So as you start to venture out after the conference today, I understand you guys can roam around for lunch. Drive up Broadway or walk up Broadway here. There's a plaza, and it's the largest plaza in the state of California. It's the only plaza in the state of California that you're allowed to have open alcohol containers, mostly because it's wine country, wants you to enjoy yourself there. But that's also where the bear flag was created. That's where the battle took place. And then after the battle of the state of California, and then the battle of the Bear Flag Republic flag, then the county was here. And I'm sorry. And then after the county, the Santa Rosans came down, which is the next city up from us, came over, took our county seat, and what was left here was just a nice, beautiful city known as the city of Sonoma. So again, you guys are in for a real treat. Restaurants are in walking distance, attractions are in walking distance, wineries are within walking distance. So if there's anything that we could do for you, I know we've put together a packet with our visitors guides, our winery maps, and some other destination information. We welcome you. We would like to have you enjoy yourself. Our visitor center is actually in the middle of the plaza. It's about a half-mile walk, or excuse me, about a mile walk up Broadway here. Once you get there, restaurants, wine tasting rooms, our visitor center, we're here to help you guys. So enjoy the weather, enjoy yourselves. You're at a beautiful resort and in good hands. So thank you.
Thank you, John. Thanks for the intro to Sonoma. Okay, so just kind of follow up on that, I suppose. So the some details about lunches and so on. So lunches for this conference are going to be on your own. We do have the hotel concierge, so we encourage you to get recommendations and make reservations to the concierge where possible. There is a shuttle from the hotel. It's an on-demand shuttle, so you can please go to the concierge and reserve it. The shuttle goes back and forward to the square. It's about a 5-minute round trip, so you should always be able to get the shuttle easily from the hotel reception. The walk, if you want to walk, it's about 18 minutes. So we're going to have a two-hour space for lunch, so that would give time to walk if you did decide to do that. And then there's also taxis and Ubers available as well. Okay, so I think Jeff will talk a bit about the schedule.
All right. So just wanted to basically give you a bunch of little nuggets of information, some of which I know you're very much looking forward to. But first, we're going to talk about the schedule. First of all, if you want to get a really detailed view into the schedule, we are using the Conference Navigator, which is courtesy of Peter Brusilowski's group. There's some very cool visualizations and other things. You can use that short link to get to it if you want to. Just to give a brief overview of what the schedule will be, obviously we have a keynote coming up just in a second. We have a bunch of technical paper sessions today. Later this evening, we have the demo and poster reception. That's in a place called the Stone Room. It's kind of in front of the lobby. It's the big stone building when you walk out the front door. We'll have SVs and signs also to get you there, so should go pretty easily. Tomorrow, again, a lot more papers. We'll also have a banquet, cocktail hour. So the first hour from 6 to 7 is the cocktail hour, and feel free to come anytime during that period if you want. And then we'll have dinner following that starting at 7. It's a buffet. Then on Wednesday, we have our second keynote by Elizabeth Andre, more technical paper sessions. And one thing I want to emphasize about Wednesday is that we'll have a town hall. That's where we'll introduce the next couple IUI conferences, and that's where you have the opportunity to voice your feedback on the conference, which I'm sure will all be good. And then on Thursday, that's when the tutorials and workshops in the student consortium are. We ended up having to reverse that from typical years. Usually it's before. This year it's obviously after. Had to do with the hotel, but actually we're looking forward to kind of seeing how this experiment works out. I'm sure this is probably the slide that everyone's been waiting for, which is the Wi-Fi information. So if you want to get on the Wi-Fi in here, if you're a guest of the hotel, you can also use the guest network. But this, I'm told, will give you the best bandwidth possible. So if you use the Renaissance Conference Network, IUI 2016 is the password. There is also, when you go to do this, there's an ominous purchase button. You're not purchasing anything, so don't worry about that. One thing we'd really like to encourage you to do while you're here at the conference is to be social on computers. So on social media, use the hashtag IUI 2016 on Twitter, Instagram, wherever you want to use that. We do have a Twitter account for the conference, ACM IUI. We're going to try to have that tweeting during the conference, various live tweets. You can also go post stuff on our Facebook page, which is also Facebook/ACM IUI. And finally, this is something we are very much trying to experiment this year, which is that we are live streaming the conference. This came together very late, so this is one of the first times we're telling you about it. You can go view the stream at that link. I would appreciate it if you did not view the live stream here in the room, just to keep the bandwidth down. But you can please do send this out to all your friends, broadcast this widely, tell your colleagues back at at your home institutions about it so that we can get some people watching. It is, as I said, an experiment. We just pulled this together, like literally in the last 5 minutes. That was all the testing you heard prior to us getting up here and talking. So there are likely to be technical issues as we go, but we're really excited about that. And thanks very much to David who put a lot of this together. All right, one last thing I think, which is that if you need anything, an issue comes up, you have a question about something, please go find our student volunteers. They are wearing the beautiful bright green shirts. You can see a couple student volunteers around here already that are wearing those shirts. When I mention the student volunteers, I really want to thank both the SIG-Chi Development Fund and also SIG-AI for providing travel grant support for the student volunteers. We have a lot of student volunteers, 19 of them, and that's all thanks to travel support from those two institutions. So thanks very much to them. All right, and now your program chairs, Christina Canati and Massimo Zancadaro.
Hi, welcome. And I would like to introduce briefly the program. We have an amazing program this year. We got 194 papers, more or less in line with the other years. And the review process was very long and difficult, but eventually it got very smooth. We have a 25% acceptance rate. 5 papers were shepherded and eventually accepted. And again, the 25% acceptance rate is in line with the last year, so we are happy with this program. In particular, we had 112 submission of long papers, and the acceptance rate for long paper has been 23%, and 82 submission as short papers with an acceptance rate of 28.
And as Massimo said, we had a fairly convoluted review process, compacted in a very short period of time. So we want to thank all the participants because they had to be really on top of all the deadlines, and they were. So it was really smooth, although again compacted into about 4 weeks. So for every paper, we had 1 senior PC member at 2 to 4 PC members assigned. It was a double-blind review process. They generated reviews. On the initial reviews, there was a first round of discussion. Then the reviews were sent out to authors who had a chance to rebut if they wanted to. And that generated a second round of discussion, after which the senior PC member would generate the meta review and a recommendation for acceptance or rejection. At the end of this process was an online PC meeting during which we met with every single senior PC member to discuss the papers that they had looked at and that generated the final outcome. So again, our reviewers did an amazing job. So we had about 34 senior PC members and 84 PC members. These are all the names. Of course, we don't expect you to read them. They are on the website. But again, I want to thank them because they did an amazing job, very reliable, very, very professional. So, and I want to thank Massimo because it was a great co-chair to work with, and the organizers. They also did an amazing job. That's it. Now for the most interesting part, probably, awards. So we're going to have a Student Best Paper Award and an Overall Best Paper Award. So we're going to announce the Student Best Paper Award first.
The best student paper, after a long deliberation, we had a few papers, few candidates. And eventually, we decided for TagFlip, Active Mobile Music Discovery with Social Tags, by Mosen Kamalazet, Christopher Crowley, Thorsten Moller, and Michael Sedlamer. I hope I pronounced correctly. If some of the authors is there, so please come.
Yeah, so we have a nice plaque for you guys.
Oh, thank you.
And we got photo op. Let me sit here. Because everyone wants to see us in a photo. Congratulations.
Oh, and they are presenting today in the first session, 11 a.m. And then for best paper, adaptive contextualization, combating bias during high-dimensional visualization and data selection, David Gotts, Shun Sun, and Nan Kao. And they're presenting at 3:30 this afternoon. Anybody from, there you go.
All right, so that's it for that. One reason I should note why we gave the awards out now is just because we wanted you to know what those what papers received the awards so that you could appreciate their talks that much more. So now we're going to bring up the opening keynote, and I'll let John introduce.
Okay, so yeah, it's time for our first keynote. So I'm delighted to introduce Xavier Amachin. He's going to give the first keynote of IUI 16. Many of you are probably already familiar with his work. He's well-cited work. He's particularly in the area of recommender systems and machine learning. So he has strong records in academia and in industry as well. He's currently serving as Vice President of Engineering at Quora. Prior to this, he was a Research Engineering Director at Netflix and also Technical Director of the Alisphere project at my own UCSB. Xavier holds a PhD in computer science and a degree in telecommunications engineering and currently lives in Los Gatos with his wife and 2 children. He originally hails from Barcelona, where he supports the one of the football teams over there, with the one with the stripes, I think. So today, without any more ado, today he's going to talk about the past, present, and future of recommender systems. So please join me in welcoming our first keynote speaker. Thanks. It's connected. Let me see the connection. It's HDMI. Yeah, just plug. Let's try this. Yeah, I tried it.
No, he's pressing the input button. It's confusing us.
Try that VGA one instead.
Yeah, maybe we'll just do video feature.
Okay. Hello. Yeah. So why we feel the organization first for inviting me, and also want to highlight how beautiful of a location this is. So I live in the Silicon Valley, which is roughly an hour and a half. Oh, here it is. Let me make sure. This looks kind of weird. Okay, there we go. So I was saying, I live in the heart of the Silicon Valley, an hour and a half drive from here. And one of the things you don't realize, for those of you that are not local, when you come to the Silicon Valley, is how much of beautiful nature you have around you. So you have the Pacific Ocean and things like Big Sur and so on, very close drive from Silicon Valley. you have the mountains, you have skiing locations very close by, and then you have the Napa Valley, this wine region, which is, again, an hour and a half drive, beautiful, reminds you probably of the southern France. To me, it reminds me of my local Catalonia, or the regions, the wine regions near Barcelona. And I do recommend that you guys take a walk or a bike ride or whatever around here, because it's really beautiful. So thanks, John, for the introduction. I'm going to go a little bit more into telling you who I am, because for those of you that know me, especially from my last few years of work, you might consider me a cold-hearted, ruthless, machine learning algorithmic guy. And I have to admit, there's part of that is true. So there's a lot of my work going into algorithmic machine learning. But I've been in academia, and I've been doing very different things. And I think many of the things that I'll be talking in this keynote that relate algorithms to how we perceive these algorithms through the interface and so on, they also respond to how I've come to where I am right now. So a little bit about me. I actually did my PhD on music technology. I don't know if you guys have heard about the music technology group in Barcelona. It's pretty well known. It's one of the top 5, I'm pretty sure, in the world. And I was working at that point in the intersection of music, software systems, signal processing, and also we did a lot of work in defining interfaces for how to define complex music systems and signal processing systems. So that's what I did in my PhD. I actually developed an open source framework that was pretty successful at that point. We haven't maintained it that well. It's called CLAM. Then I moved to UCSB, as John said, and at UCSB, I was the technical director of this Allosphere, which is an amazing installation. If you guys get a chance to go and see it, it's great. It's one of the largest immersive environments in the world. It's a 10 feet diameter sphere that is suspended in a cube, and you walk into it, and you see 3-dimensional images and 3-dimensional sound, and you can interact with scientific data, like blood flowing through human body or the human brain or chemical reactions and so on. And we were working, and they're still working at UCSB, on trying to define this sort of like Uber interface for data and scientific visualization, and that's part of what I was doing there. Then when I moved to Telefonica Research, that's when I started focusing 100% on recommender systems, and I published most of my better-known papers. A lot of those papers are actually about how users perceive the interface, how they give feedback, how algorithms interact with that feedback, and how we can deal with things like noise in user feedback. You can go through my, if you go to Google Scholar, and you'll see a lot of these papers, they're from that particular time. And then I moved to the Valley, and I went to Netflix. So I was leading the algorithms team. Algorithms team was in charge of everything from recommendations to search, things like personalized search, and a bunch of other things that go into the Netflix user experience. We were doing on the back end all the algorithmic work. Recommendations, of course, is like the main thing. Like 80% of the things that get watched on Netflix come from the recommendations, so that was a huge thing. And finally, about a bit over a year ago, I moved to Quora. And in Quora, I'm leading the whole engineering organization. It's a small startup. It's only 150 people, but I lead the whole engineering organization. We do a lot of recommendations on machine learning and algorithms, and I'll talk a little bit about that during my talk today. And the real interesting thing here, which I'll mention briefly, is how do we treat all this textual data and all this user-generated content in order to create these algorithms. Okay, so with that, and because I'm pretty sure that all of you are familiar with Netflix, but not so much with Quora, just let me spend 2 slides telling you a little bit what Quora is, because I'm going to be using examples both from Netflix and Quora mostly, and Quora is probably a little bit less known. Let me have a first show of hand. How many of you are users of Quora? Okay, it's a pretty significant, maybe 40% of the audience. So I recommend all of you to go and check it out. It's free, so you can just sign up, or you don't even need to sign up to start checking it out. But Quora, it's a question. People usually define it as a question and answer site, but we think of it much more than that. If you think about the mission of Quora is to share and grow the world's knowledge. So we compare ourselves more to Wikipedia, for example, than we compare to, say, Yahoo Answers. We care deeply about knowledge and about growing the world's knowledge, and we think that most of the world's knowledge right now, it's still not on the internet. It's in people's heads, it's in books, it's on traditions, but it's still not digitalized. And one way to create that digital knowledge, which is very different from the encyclopedic approach that Wikipedia follows, is to have questions and answers. If I ask you a question about something you know, you're going to answer with some knowledge, and then I'm going to be able to put that on the internet. So that's what we care about, and we have millions of questions and answers, millions of users, and thousands of topics. Because of this mission that is related to knowledge, we care deeply about three things, and I think that sets us apart from other products and other sites. We care about relevance, and that's something that is common, right? We care about serving something that is relevant for you and that you care about. We also care about demand. So we care about all kinds of knowledge, but of course, we care more about the knowledge that most people want to know about. If it's a very niche thing that very few people want to know, we care about it, but less than if it's something that a lot of people want to know. But I think the third one is the important one. We care deeply about quality. Knowledge is something that is related to quality and trustworthiness, if you will. So we do put a lot of effort in having algorithms and having the interface and the feedback that goes into the users that actually reinforces this notion of quality and trustworthiness. Okay, so this was a little bit of a bit of a long introduction into me and Quora, but this is going to be the index of the talk. I'm going to start by going back in time, talking about the record. I'm going to walk a little bit through the Netflix prize and what happened there and how that was related to what we thought was the recommender problem at that point in time. And then I'm going to go a little bit more into the present and go beyond rating prediction, those things that were not captured in the Netflix prize. And there's going to be things about the present and the future there. And finally, I'm going to end the talk with a few lessons learned that basically connect many of those examples from the past and the present into things that we've learned through the years. Most of these things are connected to industry. As I said, I'm going to be using Netflix and Quora as examples, but of course I do have academic and research experience, so I think I'm colored by both, having both points of view. Okay, so the recommender problem. What is or what was the recommender problem? So if you think about the traditional definition, if you look up what is the traditional definition of the recommender problem, it was something like estimate a utility function that automatically predicts how much a user will like an item, right? And then it would go into saying, well, and in order to estimate that utility function, you can use things like the past behavior and the relation from user to user, the similarity between items, context, and so on. And that's pretty okay. I mean, it covers part of what is the recommender problem, let's say 80%. And it kind of leads people into this solution, which is the core of the recommender problem, then becomes a data mining problem. And you can think of it as something that you basically have, and by the way, this picture is from a book chapter in the Recommender Systems Handbook that I contributed to years ago, probably 5 years ago, where we were saying, well, the essence of the recommender problem is a data mining problem, and I still think that covers maybe 80% or maybe 60, I don't know. But the idea is you have data, you pre-process the data, you build a machine learning model. There are different kinds of approaches to do that. And then you test and validate your data, and you're done. And you have all these different methods that you can apply on the different parts of the funnel. But basically, that's what gets you, that's what's covering the recommender problem from that perspective. But the truth is, there's many other things that are not covered by this core definition of the recommender problem. And those are the things that I'm going to be focusing most of the time during my talk today. First and foremost is the user interface. Whatever you do on your data mining algorithm, if it's not also comes with some similar approach on the user interface, it's not going to matter at all. As a very dumb example, it's very dumb, but I've seen that happen in reality. If you build the best of the recommendations algorithms, but you put it below down the page where people need to scroll down for 30 seconds in order to get to it, it's not going to matter at all, right? That's a very dumb example, but you can think about a lot of relation between the user interface and the recommender system, and we'll see many during the presentation. But there are others. There's system requirements, there's serendipity, diversity, awareness, explanations. It is true that some of those can be covered and can be introduced in some of the machine learning data mining algorithms, and we'll talk about it. But the reality is that those were not really covered in the initial definition of the recommender problem. And I'm going to be focusing on those for the rest of the talk quite a bit. Okay, so this traditional definition of the recommender problem led into the Netflix prize. And the Netflix prize, although what Netflix was really interested on was high quality recommendations, how do you measure high quality recommendations? It's very hard. And how do you put out a contest where you have people provide those recommendations and you can have a quote unquote objective way to measure whether they're good or not? So the easiest way is to come up with a number and a proxy question. And in this case, the proxy question was the accuracy and predicted rating. Say, okay, if you can predict the rating better, and that's kind of like related to the utility function we were talking about in the recommender problem. And we talk about a metric like root mean square error. Well, if you get a less root mean square error, means that your recommendation is better. But it's very important to realize that even at that point, Netflix realized that was just a proxy question. That was not really what they were interested on. Now, the interpretation on the research community was, hey, this is what companies really want. Let's focus on that, and that's what really matters. We'll see why that was not the case. But going a little bit more into the Netflix prize, in 2007, so a year later, the Progress Prize, the first year, the top two algorithms, singular value decomposition and restricted Boltzmann machines, they both gave 0.89 roughly root mean square error, and a linear blend of those two algorithms brought the RMSE down to 0.88. So that was something that Netflix really jumped on right away because it was much better than what they had in production. We implemented it in production, and it's still used nowadays as part of their prediction algorithm for rating prediction. They had to, or our team actually had to work into a bunch of things like how to scale it and how to make it work when users were adding more ratings and so on. But the core of the Netflix prediction for ratings is still based on the first year Progress Prize. And that was pretty good. Now, what happened to the final prize? Because it took 2 more years to actually get to the final ensemble. And the final ensemble didn't have 2 methods, it had 103. And what happened to that? Well, the reality is that didn't really matter so much. The increase in accuracy from those 101 predictors and the increased complexity didn't make it worth it for Netflix to actually invest in productionizing all of that, putting a lot of engineering efforts into making it work. And by the way, by that time, Netflix had also realized that rating prediction was not so important, and there were many other things that were more important than rating prediction. So that's a change in focus when Netflix realized, hey, we probably put too much attention on this. And as a matter of fact, by that time, some of you might know, Netflix was about to release a second Netflix prize that didn't go through for legal reasons, but the second Netflix prize was going to be based on something different than not rating prediction. Okay, so if it's not about rating prediction, what is it about? So a few things. First of all, I get a question from people many times tell me, how is the Netflix recommendation algorithm? Or how do you compare the Netflix recommendation algorithm to the Quora one? Like if there was a single algorithm, there's like many different algorithms in play in any of these products. And that's not to say that there's many algorithms that go into an ensemble to produce a prediction, which in some cases it is. But it's more about there's like a lot of different components in your system, in your product, that are actually producing recommendations. As a matter of fact, everything you see is a recommendation. As an example, the My List feature at Netflix, I like this headline a lot because it said, Netflix thinks that they know you better than you do because of algorithms, which is true. In this case, My List, if you're a Netflix user, you'll know, is where you actually put the things that you'll watch in the future. And you could think, because that's a user sort of like generated action, users should know how to care and cater for that particular aspect, right? They should be able to sort things out and put them in the right order so they know when to use them and when they'll have them available and whatnot. So originally the list, when it was available only in the US, that's how it worked. You could go in there, you can put things around, you can move them, you can change them. We decided to do a test where we said, okay, forget about that. We're just gonna sort that using an algorithm. We're just going to predict how likely are people to watch every single thing at a given point in time. And it turned out that that was much more efficient than letting users do it themselves, right? So this is an example of an algorithm which is actually introduced in the Netflix product, which is yet another algorithm. But if you think about it, there's like even in search or in every single part, that's why when we say 80% of the things that people watch come through recommendations, it's because it's almost everything that you see is a recommendation. Okay, so this is another picture that I like to put up as a way to think about the evolution of the recommender problem. And we were talking about initially rating prediction and about the recommender problem as how to predict a number. But the reality is, over the years, we've gone and kind of like added dimensions to this problem. So we went from rating prediction into ranking, and I'll go into this a little bit more. Then we went into page optimization, and I've talked about all these things at some point in the past. I'll do a summary during this talk. And then we added context, and then it became a multidimensional problem, right? So this idea of sort of like making the recommender problem more holistic and more multidimensional and not just about one single number, I think it's a neat way to think about the evolution of the recommendation problem. Okay, so let's talk about ranking. No matter what you do with your algorithm, the reality is that in your user interface, most recommendations are going to be presented in some form of ranked list. So that means that you should be able to interpret your recommendation as a ranking problem. Now, if I have to come up with a ranking algorithm, my initial first recommendation as a baseline to everyone is like, think about popularity. Just use popularity to start with and then build from there. And why is that? I mean, the reason is if I have to come up with a list of songs that I'm going to recommend to you, for example, I don't know anything about you. The best thing I can do if I don't know anything about you is just go to the most popular songs right now and say, hey, I think you're going to like this. And chances are, just because of how statistics work, that you're going to like some of that stuff if you're on the average of what most people like, right? So beating the popularity baseline, sometimes it's not as easy as it seems. And that's when personalization kicks in, obviously, right? Anything that you add to popularity is going to personalize and going to make things better. But I find it pretty amusing to see how many people don't compare their things to the obvious popularity baseline to say, hey, are you even doing better than that? Don't compare to another algorithm. Just compare to the baseline of popularity and see how much better are you doing. Now, what about rating predictions? Because rating predictions, you'll say, well, that's a number, but I can use that for a ranking. And of course you can, right? So basically, you just predict the rating, and you rank things based on their predicted rating. Here's an example of movies and rating prediction. What happens in this case is that higher rating predictions tend to be dominated by niche titles. And there's a reason for that, right? There's some, for example, in the case of movies, there's some genres like anime where there's a very niche set of people that watch those titles, but they're all super enthusiastic about those titles, and they rate them really high. There's many such effects at Netflix that were very clear. And therefore, it's very hard to predict a low rating for that title because you basically don't have anything on your data set that is going to tell you that that rating, that movie is going to be low, is going to deserve a low rating. So predicting by rating prediction doesn't tend to work that well. As a matter of fact, I'll tell you one thing, it usually works worse than the unpersonalized popularity baseline that I mentioned before. The other reason it doesn't work is because of the objective function. When you're optimizing, and you're predicting a rating, you're optimizing for noise or an error metric like a root mean square error. Root mean square error has nothing to do with ranking, and it's actually really bad for ranking. One way to think about it is you're going to be assigning the same kind of weight to an error that you make when you're predicting a 4 instead of a 5 than when you're predicting a 2 instead of a 1. But the reality is that 2 or 1 prediction is never going to come up in a ranking. Because if you're going to rank the top, say, 100 or even 1,000 movies, those things that are rated 2 or 1 will never make it into your ranking. However, a change in the top of your ranking, something that should have been predicted 4 and it was predicted 5 or the other way around, that's going to have a huge impact on your users. So root mean square error doesn't work for ranking. Okay, so rating prediction doesn't work very well. Popularity is our baseline. And I hear you say, okay, I got you. Why don't I combine those two in a single function? And that's true. That's how all good things get started. You just combine those two things, get the best of one and the best of the other into a single model, and there you go. So let's think about this two-dimensional space where we have predicted rating and we have popularity, and put some movies in here, and I'm going to try to build a linear model. A linear model that basically combines the popularity of a given item or a video and the predicted rating for a video for a user, and I'm going to assign weights to each of those. Now, the key thing in all these models is how do you find those weights, right? Does popularity matter more or less than predicted rating? And how do I find that out? Another way to think about it is like, this line is going to have a slope. How do I find the slope? Well, you find that slope by basically regressing on your data, right? You have a lot of examples. You have data that is telling you, hey, this is how people react to the popularity and the predicted rating. So I can build a model, and I can just regress my model into the data that I have. Once I build a model, once I know the weights, once I have that slope of the line, what I can do is just project the items that I have onto that line, and there I go. I come up with a final ranking. So it's as easy as that. I built my first learning to rank approach using the two dimensions that I had at the beginning, which were popularity and predicted rating. I've repeated this several times and different conferences, but I think it's such an important lesson to be learned, because it's like everything you build, it's going to be built upon this. This is an amazing sort of model where you've built in your baseline, which was popularity. You've introduced personalization through predicted rating, which was your initial definition of the recommender problem. And now you have a multidimensional model, simple linear model, that is able to beat the baseline for sure, because the baseline is included, and it's also personalized. So, of course, by the way, the key here is, now that you have these two dimensions, why stop here? Why not add many other things? Why not add demographic data from the user? Why not add whatever you know about the user or the video, or metadata, or whatever? It's like you throw everything in, and instead of having two dimensions, you're going to have hundreds, but it's the same idea. So learning to rank is a machine learning problem, and the goal is to construct this ranking model. The training data can be either the partial order of things that you have, Or binary judgment, you can have positive and negatives. You can learn these models, like the one that I mentioned. The simplest approach is doing a standard supervised classification problem. So you can learn that model using a standard logistic regression. But then there's a lot more research going on in the community, and you can get fancier than that. And you can, popular models for learning to rank, like lambda mart, for example, are very typical. Those are going to probably get you a little bit better, but you can go a long way with a linear model for that. The other thing worth mentioning here is the metrics. As I said, RMAC is not a good ranking metric, so then you need to learn about what is your right metric. And there are several, or many, I would say, like NDCG, mean reciprocal rank, fraction of concordant pairs. Now, those metrics, each one of them has a different set of properties, and I can't recommend you one because it really depends on your problem and on your user interface. Some of them are going to be weighting much more errors made on the head of the ranking versus errors that you make on the middle of the ranking. Some of them are going to be flatter. You need to look at the response of those metrics and realize, does it make sense? What is it? How many items is my user going to be seeing on average? And how much weight do I need to put on making an error at the head versus somewhere else in my ranking? The other thing you can do is just use them all and see how they correlate to your user behavior, of course. That's what most people would do. Okay, an example of, a non-obvious example of ranking, for example, is the Quora feed. When you open your Quora app or your Quora homepage, you'll see a bunch of stories, and they're all ranked for you. That's an example of recommendation turned into ranking. It's more interesting than the standard set of ranking that we would do at Netflix for several reasons. One of them is we have to rank two different kinds of items. We call them stories, but in reality it's two kinds of things. It's questions and it's answers, and we want to mix them all up in a single ranking function. And then there's the question of, like, what does interesting mean in the context of Quora? So interesting mean you're interested in the topic, you're interested in the person who wrote it, or it's something that is timely and people are talking about Donald Trump and you want to read about Donald Trump. There are many things that go into play into what we're optimizing for in this ranking function. But at the end of the day, it's yet another approach to personalize learning to rank. And of course, when we measure that versus the time order ranking that we could produce just like Twitter does, there's a huge change in engagement, right? So it's clearly something that we definitely need to do. Okay, let me get some water. Similarity is another of those forgotten topics in the context of recommendations. We use the notion of similar as a way to recommend things all the time in many places, right? In the context of Netflix, for example, in response to many user actions, when a user was adding something to their list or was searching for something, you will get a dialogue saying, hey, you just added this. There's a similar stuff that you might be interested on. Or you just finished watching something. Here's some similar stuff that you might be interested. Or even in the context of in your homepage, you'll get more like whatever, or because you watch this rows that are basically based on this notion of similarity. At Quora, we have the same thing. We will recommend you related questions. If you're reading an answer to a question, we're going to tell you, hey, you might be interested in this other question that is similar. Now, there's always the question about what does similar mean? Because if you think about Quora, we could do just a textual, perfect textual similarity function, and would that be good? The answer is no. When we talk about similarity, we're also introducing this notion of it needs to be similar, but it needs to be also interesting. As a matter of fact, if it's too similar, it might not be interesting anymore because it might be a duplicate of what you're reading. So it's like, sure, I don't want to read the same thing again. right? So you need to think about what am I optimizing for in the context of similarity, and how can I come up with something that actually engages users more. One way to think about similarity is always to think about this graph-based approach. So this idea of you have all your items in a graph and you're basically producing these values of edges between one item to the other one. As a matter of fact, one of the well-known approaches to measuring similarity is this SIMRank approach by Jay and Widom in 2002. So SIMRank is basically the notion of page rank translated into similarity. And the basic hypothesis here is two objects will be similar if they're referenced or linked in that graph by similar objects. And this is a very good approach. It's not very efficient, but there have been some updates to it that make it more efficient. And you can build similar approaches based on graph-based approach that work pretty well. But I think the key to similarity is because we don't know what it really means for the user, we need to introduce different variations of it and learn from the user and what they mean by it. So when we talk about similarity, are we talking about similarity in the metadata or in the tags or in the text itself? Are we talking about similarity in the way that users play a given title or similarity to the way they rate something? We don't know, but it really doesn't matter so much. We can just build a model for each of our notions of similarity and then learn the combined weights, just as we did before with the popularity and the ratings, and let the users vote on what really matters. And this let the user vote can be done different ways. It can be done by looking at the data and learning the ensemble. It can be done by doing A/B testing, or it can be done by doing some multi-arm bandit, explore, exploit. I'll talk a little bit more about that later on. And finally, again, similarity emerges as a concept from the user perspective. It's not a preconceived notion that you have in your head of like what is similar and what is not. And sometimes you are surprised because two things are considered similar by users that in isolation in a lab you wouldn't say they're similar. Okay, social recommendations. So this is something that was also missing from the initial definition of the recommender problem, although it did mention that you could be basing your recommendation based on relations between users. But the reality is sometimes users are themselves things that are going to be recommended, or or they are things that, there are entities that are going to be very important in order to define how the algorithm behaves. And that leads to social recommendations. So, for example, at Quora, we do recommend users themselves, right? We want to strengthen the social graph of people that you follow, and we're going to recommend you users to follow based on topics, on user interactions, on user-related features. We also are very interested in inferring this notion of trust or expertise in the social graph, because that's going to influence and impact all the different algorithms and all the different aspects of how much we trust the quality of a content to be true, but also how much are we going to be recommending you something that was written by somebody. Depends on the trustworthiness and how you are going to be interested in the user who generated that content. So this leads to this notion of social or trust-based recommender problems, where you can think of trust as this notion of social proximity, like how close in the network, in this network that you're building, and given some edges that are weighted, how will I trust something that comes from that source? And there are many approaches to this. I'm not going to obviously go into detail, but some of them from the literature, probably, or maybe you're familiar with, like Avocado or Appleseed, Mole Trust, or Title Trust from Goldbeck. They're all different ways that you can implement another form of graph-based algorithm, different from the similarity one, for trust-based recommendations. Now, the interesting thing, as I was saying when I was talking about social trustworthiness in the context of Quora, is that you can feed this into other forms of recommendations. So, in particular, many forms of algorithms use the notion of similarity between users, and they have different ways of computing that similarity. You can replace that by the social similarity, and there's several papers in the recent literature that have done that. Or you can even introduce the social connection as a part of the objective function. If you're doing, say, a matrix factorization or something like that, you can input directly the social connection strength as a way to either regularize the objective function or introduce it as a weight itself in the objective function. So there's like different ways that you can introduce the social effect into a collaborative filtering approach, for example. Okay, explore, exploit. I talked a little bit about that before, but what is this about? So another of the key issues here when building any kind of recommendation system is how to trade off between exploration and exploitation. Exploration means I'm going to choose the next opportunity that I have with the user to learn. I'm going to use that occasion to learn more about the user. I don't care if I get it right or wrong. I'm just going to explore. Exploit is the other way around. It's like, okay, I'm just going to make sure that I get it right. I'm going to give them whatever I know about or the little I know, but I can't really take a chance and miss this opportunity. The problem is you want to have an informed way to trade off between these two things, learning about the user, exploring, or learning about the item and exploring and exploiting. So how do you do that? So there are different approaches, but the best one, to my knowledge, is to use multi-arm bandits. Multi-arm bandits, I don't have time to go into a lot of details, but I'll tell you a couple of things that I hope are going to be enough, is this idea of sort of like having your slot machines and selecting which arm you're going to play on at every point in time. You know that some machines are giving you good money, but others you haven't even tried. So it's like, should I take a risk and explore another machine? Or should I go for the one that I know is giving me good prices? So the naive strategy for this is epsilon greedy. And this is, I think, the easiest way to understand multi-arm bandits. Epsilon greedy means with a very small probability, epsilon, say 5%, I'm going to explore. So the next thing I'm going to show my user with 5% probability is going to be something that I have no idea if the user likes or not. It's just going to be something I explore on. With 1 minus epsilon, with a very high probability, say 95%, I'm going to exploit and show the best thing that my prediction algorithm is telling me I have for that user, right? So that's a very simplistic approach. Doesn't work that well, but it's a good way to understand it. There are many better approaches like UCB, upper confidence bound. And the best one in practice, which I would recommend just with my eyes closed for most of the applications, is Thompson sampling. It's a very simple algorithm that all you need to do is have a posterior distribution that you're basically updating every time that you show your next item, and it works really well in practice. There's a bunch of papers, I'm going to share the slides so you'll get those papers, that talk about how to use explore exploit in recommendations. There's this presentation by Deepak Agarwal from LinkedIn talking about explore exploit approach to recommender systems, where he talks about Thompson sampling and similar approaches. Okay, and I'm finishing here with the sort of like my journey into more dimensions and sort of like more complex things going into recommendations. Page optimization. So the ranking problem is something that is going to get you through part of the problem, which is like, how do you come up with that list of things that I'm going to recommend? But if you think about any page, for example, the Netflix homepage, it has a bunch of different ranks list that you need to optimize in this two-dimensional grid. So how do you do that? Well, it turns out there has been some research, not a lot, so this belongs more to the future than to the present, but there's some research. So for example, Dimitri Lagun, who is now at Google, did this PhD thesis about modeling user attention and interaction on the web. He also has a bunch of papers and best paper awards that you can find online. And he studied like how do users pay attention to different kinds of web pages. And he came up with this very interesting plot in his PhD thesis where he was saying, well, this is where people look at in web search. This is what people look at in Twitter or Amazon, on CNN. And you can build attention models from that and then feed those attention models into your page optimization algorithm in order to define like how much do you need to weight the different things that go into your algorithm depending on the position where they're going to be clicked on. Now, there are more things, and things that are more complicated than that, because it turns out that you need to trade off a bunch of things in your page optimization algorithm. Things like accuracy versus diversity, very important topic. You don't want to show many things that look all the same. Discovery versus continuation, which is similar to the explore-exploit trade-off. Depth versus coverage, and so on and so forth. As I said, not much research going on, or not much research that has happened in this area, but this is an old paper, this Fair and Balance by Smola and some of his students. This is a new one. This is actually, this paper won the Best Paper Award at Wisdom this year, 2016, and I was very impressed and interested to see that there was a paper on page optimization that actually won the Best Paper Award at Wisdom, because I think it's a very interesting area of research and a very interesting topic. We've been doing a lot of things in the industry to deal with it, but there's not so much research in academia sort of like setting a good basis for it. Okay, so with that, what are some of the lessons learned through all these years? Okay, and some of this are going to be maybe a little bit controversial or interesting, or some of them might sound well known. First one, implicit signals beat explicit ones almost always. So I think many by this time have acknowledged that implicit feedback is more useful. And by implicit feedback, I mean the kind of feedback the user gives to the system without really realizing that they're giving feedback. Just clicking here, scrolling there, using the site, versus the explicit one, which is like, I'm going to give you feedback and I'm going to say, this is 3 stars and I really like, or this is 5 stars, I really like it. So Netflix has talked about that. When I was there, we talked about beyond the 5 stars. YouTube actually changed from 5 stars to thumbs up, thumbs down. So is implicit feedback really always better? And if so, why? So the reason implicit data is usually better is because it's more dense, it's available for all users, and it's representing better what users do versus what users want to say they do, right? So you'll get a bunch of very high ratings for documentaries on Netflix, and then people at night when they're brain dead, they'll go and watch Hot Tub Machine, and that's okay, and they want to watch that, and they won't give it a high rating, but still something they want to watch. And it's better correlated with your with your behavior. One way to think about it, if you, I'm pretty sure you can't see this, but this is comparing this picture here on the left is comparing what happens if you look at the top rated movies in IMDb in 2014 by rating or by box office. By box office, you find things that I could recommend to most people in this room, and I think you would agree that they're more or less okay. You would go and watch in the cinema. The ones that you get by rating, they're really niche things that I'm sure there would be 2 or 3 people in this room that might find it interesting to go and watch, but most of us would say that's really weird. So this is related to the density and the availability, how much sort of like explicit data represents your overall population. However, and this is the key thing here, it's not always the case that your implicit data correlates to long-term user retention, and that's a really important thing that you need to take into account. A clear example of this is clickbait. I can always introduce things in my system that are going to make people click, but long-term, are not going to correlate into making my users happier. And we've seen this at Netflix, at Quora, many companies that have gone down just basically because they were just optimizing for more and more clicks, and all of a sudden, users were not there anymore. Because, yeah, you can get a bunch of clicks from a user if you put some shiny, sort of like easy-to-trick thing, and you'll click 3 times, but the third time I'll say, what am I doing here? I'm wasting my time. I never want to come to this website again. And you'll lose the user, right? So you can't trust implicit data only. You need to think about how that correlates into your long-term metrics. I think the key issue is actually to combine both implicit and explicit data. If you look at Quora, for a given answer, we have a bunch of different actions the user can take. Some of them are explicit, some of them are implicit, and we combine them all into one. Okay, I'm going to go quickly because I think we're running out of time. Second lesson is to be thoughtful about your training data. It's sometimes not easy to define what is a positive and what is a negative in your training data. And that's something that is going to condition what your model is going to learn at the end. As a matter of fact, I like to say that your model will learn what you teach it to learn. And that's basically 3 things: your training data, your target function, and your metric. Here's an example, a made-up example. If I really want to learn a model, what I need to tell it is something like, optimize the probability of a user going to the cinema to watch a movie and rate it highly by using purchase history and previous ratings, and use NDCG of the ranking as a final metric, only using movies rated 4 or higher as positive. That's a good definition. If I leave anything out of that is not there, I run the risk of optimizing to the wrong thing. In Quora Feed, we do the same thing by actually having a weighted sum of actions where we're optimizing to different sets of actions that come from the user on the Quora Feed. Okay, number 4, explanations may matter more than the prediction. So I think that's not a new thing for you. Any of the products that you're using will have explanations for your recommendations. At Netflix, there's a bunch of explanations here, from the predicted rating to the different descriptions that you have on the movie to things like what this recommendation is based on. Same goes for Quora. We give you a bunch of context on why you would be interested on that. As a matter of fact, I'm not going to give you details on that, but take my word on it. Sometimes tweaking the explanation, even in an unfair way, can produce more results than tweaking the algorithm itself. So that's a very surprising thing. And of course, you don't want to tweak the explanation in such a way that long-term, as we said, you lose your user. But it's really impactful, sometimes even more than the prediction itself. Okay. The presentation bias is very much related to page optimization, but it's this notion of users can only click on whatever you show them, and simply treating things that you show as negatives because the user didn't click on them, it's not going to work. And there's a long explanation for this, but the simpler one is you're showing things that the model thought were good. The fact that the user didn't click them doesn't mean they're not good. This means the user at that particular moment didn't have the time or thought there was something better. You need to do things like correct for the probability of a user on the position or explore exploit approaches. Not much research also in this space. One interesting paper, not that this approach particularly works well, but it's interesting in itself, is this idea of corroborative competitive filtering using this notion of presentation bias. And the final one, which I think is a corollary to everything that I've been saying, is the UI is really the only communication channel with what matters the most, which is the user. Anything that we've talked about, like explanations, implicit, explicit data, what you're optimizing for, long-term versus user, short-term implicit feedback, this all goes through the UI. As a matter of fact, the UI is a two-way channel, right? So basically, it's the channel from which the algorithm takes the data in order to optimize whatever, but it's also a channel through which the algorithm shows the results. So those two things need to be taken into account. And many times we've seen in practice in industry, changes that we did to the UI needed to change the algorithm and the other way around. So as a conclusion, that's pretty much my conclusion. As I said, recommendation is about much more than just predicting a rating. And all forms of recommendation require a tight connection with the UI to, on one hand, capture the right kind of feedback, and on the other hand, present the recommendations correctly. Okay, with that, if there's any questions, you can ask me now or you can ask them on Quora. Thank you.
Thank you. Thank the speaker, everybody. Thank you. So we don't have too much time left for questions. We have to go into a coffee break soon, but so we're going to ask for all questions, for the format for the whole conference, that people come up to the center. And we'll also ask the session chairs of the future sessions to kind of enforce the same thing.
I have a really short question. I'm not sure it works. It looks like you claim that using RMSC and the rating is actually not a really good thing. There are many more things. Yet, do you think that Netflix price and the focus on RMSC was useful for recommender system field as a field? Or is it actually harmful? What do you think?
It's a good question. I mean, I always say the Netflix rights was not only useful for the field, but it was also very useful for Netflix. So it wasn't, as I said, the algorithms were used in practice, first thing. Second, it brought attention of the research community to a problem that then it got expanded. Maybe brought too much attention to one particular definition of the problem, but I think overall it was positive on both ends.
This one's a bit dry, but you mentioned using, for instance, box office as a popularity measure. But what other metrics have you used in the past to measure popularity, like number of ratings or just in your experience?
Yeah, it's a good question. So there's so many definitions of popularity. I simplify to say popularity, but popularity can, just as many other things, can be defined as many things. One particular thing you need to be careful is on what window of time do you define your popularity on? Is it popular today? Is it popular the last week? Is it popular the last month? The truth is, you don't need to go for only one of them. You can use all of them and throw them as different signals to your model and have your model learn which one is the one that matters the most. Does that make sense?
So yeah, thank you. That makes sense.
Okay.
Questions?
Hey, Xavier. Thank you for the fascinating talk. Stephen Chan from Grouplands Research. So you mentioned about how important the explanations are in recommender system, right? So in your job, have you looked at this trade-off between how much information you provide in your explanations versus how fast you want users to browse through the whole entire page and just browsing through different options there?
Yeah, it's a good question. I mean, information overload of any kind is going to make users sort of like not only take more time, but actually come to a basically point where they paralyze and they can't act because they have so much information. So I don't have a very informed solution to that, except that this is A/B tested constantly in different products in order to make the right trade-off. So for example, people ask me nowadays about what do I think about the new icons or responses that that Facebook has introduced besides the like button. I think that's a huge overload in terms of sort of like how users need to think about giving feedback. I think there's a lot of positive, but there's also the risk of like people paralyzing and not giving enough feedback just because they need to think too much about what to do. So it's not an easy thing, and I think it's very dependent on every specific case, and you do need to strike the right balance. I always strive for simplicity, so the less that you can do, the better, but that less needs to be sort of like unique and impactful.
Thank you.
One last question.
Thank you. Max Harper, University of Minnesota. So I'm interested in the idea of explanations, and you kind of flew by it. One thing that we've found is that recommendation models are often kind of black boxes. That is, a lot of data flows into them, and then ranked list pops out. And oftentimes it's hard to understand the reason behind that ordering. And so when we build explanations, they're often somewhat disconnected from that recommendation model. Like we build on top of that our own reasons why we think that the user might be interested in the thing that's actually independent for why we recommended it. Is that what you also have done at Quora and at Netflix? Or are you somehow able to reach inside your models and provide sort of what I would call honest explanations?
I'm not sure I believe so much in the concept of honest explanations. There's many explanations that go on into any recommendation. If you look at here in this case where the Netflix explanation, this is not only the result of a single model that is explaining things. There's a bunch of things going on here with many different models and different reasons. So the truth is, the reason why you might want to watch this right now can be so different. It could be, oh yeah, I know this actor, I really love this actor. Or it could be like, oh, this is really a highly predictive thing. Or, hey, I put this in my instant queue and I forgot about it. Thanks for reminding me. So this idea of like there has to be a single explanation that gets it right, I think at some point we might be able to reach out inside not only of the algorithm but the user's brain. But for now, we're better off sort of like covering wide spectrum of different reasons why the user might feel motivated to consume something or just take an action.
That's cool. How do you pick if you have all these different reasons?
It's a good point. So we usually have sort of like a meta model that picks which one makes more sense. So for example, I could have a social reason and a rating reason. If the rating reason is not good enough, I'm going to go for the social one and say, yeah, there's no way you're going to want to watch this because of the rating, because my predicted rating for you is 2 stars. But hey, a bunch of your friends watched it, so maybe you're interested, even though it's a crappy movie, right? So, and that's true in real life. There's different reasons why I watch something. Something is because it's really good. Something it's just because I know my friends at the office are watching it and I have something to talk about.
Thank you.
Can we thank the speaker one more time? And also, can the speakers for the next session please stay behind and talk to Barry Smith? And there's coffee outside. The next session starts at 10:25. So I think what we should have done is during the intro, I should have had you set up the laptop. My apologies.
Well, it's okay. It's fine.
Minor thing.
Yeah, I think we went a little bit over time. But
Yeah,
Guys, I
Yeah,
did
we
read that slides. Could you share the slides? If you can share publicly, could you share
yeah.
privately?
No. I
First
can.
of all, share the slides. I will tweet them and whatever. Get it from the what is that?
I mean, I can send you. Yeah, I'll put them on
Well,
SlideShare.
SlideShare is that is great.
the whole talk will be streamed on YouTube as well.
Yeah, I know, but it's just